Hi there, this is Penelope. This is the third short video in a series of videos on force for the Level 4 Foundation program here at WellTech. We're going to look now at equilibrium. And equilibrium occurs when an object's at rest or when it's moving uniformly, as described by Newton's first law that we saw in an earlier video. An object is described as being in equilibrium when both the resultant force is zero and the sum of all the torques acting on it is zero. So that means that, and this is mathematical notation, that says the sum of all the forces is equal to zero and the sum of all the torque, which we looked at in a previous video, is equal to zero. On the left-hand side here, this means that the acceleration is equal to zero, so the object is either stationary or it's got uniform motion. So it's not speeding up or slowing down. If we're looking at the torque, with the sum of the torques being zero, then that means that the object won't twist or turn. So that the clockwise moments equal the anti-clockwise moments. Many everyday situations involve objects in equilibrium. For example, this is one that we're going to look at. A painter organising trestles and planks. He needs to have his system in equilibrium. An engineer working on the design of a bridge, they need to have that in equilibrium. Let's have a look first at three forces, and let's have, so we've got the horizontal axis, got the vertical axis, and suppose we've got a force upwards of 5 newtons. We've got a force this way of 12 newtons, and we've got a force this way at an angle of theta of 13 newtons. So the resultant of these three forces is zero because it hasn't gone anywhere. The 3 points are balanced. They give a closed triangle. So we need to draw that triangle. So we've got 12 newtons that way. We've got 5 newtons that way. And then the resultant, well, the connecting one's got to be that one, which is 13 newtons. And there's some angle that we don't know what it is. So we need to find theta. Okay, a little bit of maths here, a little bit of trigonometry will tell us that tan, or the tangent of theta, is equal to the opposite, which is 5, over the adjacent side, which is 12. And if we do the maths on that, that's 4167. And then using our calculators, we can find that theta is 23 degrees. So there we've used what we know about triangles to find the angle that makes those three vectors, those three forces at equilibrium. Let's have a look at a second example here. We've got a ruler, and we just say that it's got negligible mass because that just complicates matters if it's got some mass itself, and it's pivoted at a point P that's 20 centimetres in. Now I'm going to change 20 centimetres to 0.2 metres. So that's 0.2 metres there. And we're going to hang a mass of 15 metres. So there's the end. It's a metre long. Then I'm going to hang a mass there at 0.8 metres. I'm going to hang a mass there, and that's 15 newtons there. And the question says what weight has got to be suspended at the 10 centimetre mark. And again, I'm going to change that to 0.1 metres, and I'm going to put a little box or an object there that's got that. So we need to find if W, the sum of the clockwise moments must equal the sum of the anti-clockwise moments because it's suspended. So let's first look at the clockwise moments. So that's force times d, force times the distance. In this case, the force is 15, so this is the clockwise one. This is 15 times. Now, that's suspended at the distance of 0.8 minus 0.2 because the pivot is at 0.2. So that's 15 times 0.8 minus 0.2 is 0.6, which equals 9 Newton meters. Now, going the anti-clockwise moments, again it's, but this time, I'm just going to move over here a bit, this time we don't know the force, so we're just going to call it FW, but we do know the distance. This time it's 0.2 minus 0.1. Okay, 0.2 minus 0.1 is 0.1, so it's 0.1 times, times FW in Newton meters. Now, the two of these have got to be equal, so 0.1 times FW has got to equal 9. Therefore, using your maths, FW has got to equal 9 over 0.1, which gives us 90 Newton meters. Now, I'm just going to see if I can insert a slide. Yes, so ignore that. Ignore my, and okay, that's fine. Now, what we need to do further though is that these two weights add to give a total force of 105, because that's 90 plus 15, and it's acting downwards on your P, on your pivot P. There's also got to be a reaction force. And the reaction force is also got to be 105 newtons. So what we've got is overall the forces acting on the ruler are 105 newtons upwards and 105 newtons downwards, because the meter rule is in equilibrium. It's not falling around all over the place. The centre of mass, what we need to look at here is that the weight of an object acts down through its centre of mass. So the centre of mass, say on this little piece of a ruler, would be in the middle there. And the weight's going to be what is acting downwards. And this is the pivot point where the object will balance, or if it's suspended, it's where the object will be in equilibrium, it won't be moving. Now, we've got here a house painter. He uses a uniform wooden plank, 2 meters long, 300 newtons weight. It's supported at both ends by trestles, and the painter, whose weight is 800 newtons, stands 0.5 meters from A, and you're asked to find the size of the forces that are acting at each end. So we've got now I can't draw very well, we've got trestles holding it up at A and B. He's standing half a meter from the end, and it's 800 newtons, and the whole of the wooden plank is 2 meters long, and the weight itself is 300 of the plank. Now, what we need to do is to look at that more in diagrammatic form. Take the man away. And so what we've got is the 2 pivots. We've got, this is 800 coming down, 0.5 meters in. Now it's about halfway. We've got 300 because that's what it said there. So that will be at a meter because that's halfway, and the whole thing is 2 meters. This is force A and this is force B. So to find the size of the force on the pivot B, we need to take the moments about pivot A, and at that point at B, the force A produces no torque because it's acting through A. So there's no distance in that sense there. So the clockwise moments are going to be 800 times 0.5 plus 300 times 1, which is going to be 400 plus 300, which equals 700 Newton meters. The anti-clockwise moments are going to be FB times the whole length, which is 2 meters. Now, clockwise has to equal anti-clockwise, so 700 has to equal FB times 2. FB equals 700 over 2, which is 350 newtons. Now, to find FA, we figure that since the plank is in equilibrium, at least we hope it is, so that the poor old painter doesn't slide off, that the vector sum of the forces is going to be 0. So that means that the sum of the upward forces is going to equal the sum of the downward forces. So that means that the forces upward are FA plus FB, and that's got to equal the downward forces of 800 plus 300, and that equals 1100. Whoops, 1100. So we already know what FB is, so FA plus 350 equals 1100, so FA has to equal 750 newtons. Now, this last one is something that you can do as an experiment, and if you've got the various measurements, I'm just going to use some measurements that I've just made up. I didn't do the experiment, I just cheated a little bit, but you do know that the anti-clockwise moments have got to be equal to the clockwise moments. So that the weight of the retort times 0.05, because it's 5 centimeters in my diagram, is 5 times 0.3. 3, 5. I'm not going to get this finished. I can use the